Welcome back. Where were you? I was waiting for you. So we're going to continue on with something that we picked up earlier, which is rocks and minerals. Earlier in the class, we looked at minerals and we looked at how they comprise rocks. And this was strictly from a geology definition. Here's my Estway rock hammer. We geologists look at rocks for the sake of looking at rocks. However, not everyone does that. There are other people who are economic geologists and the sort of general public that is interested in rocks and minerals for the economic good that they can provide for us. So we're going to look at these rocks and minerals through the lens of the economy. Let me share my screen. Where is our PowerPoint? Share. Okay, so what we're looking at now is the rocks and minerals that we looked at earlier in terms of how they can benefit us economically. And I'll tell you that this is something that is anything of value to humans that is extracted from Earth for a profit. So for example, here you see this picture that you saw before of the mineral, the geology definition of hematite, iron oxide. And we talked about polymorphism, but we geologists can look at this and marvel over how fabulous hematite is, or we can mine this and use it to make things. And we use the rocks and minerals of Earth to make things based on their material properties, which is in part why we talked about them before. So they all have different material properties. And the way that we divide the materials in our Earth is based on these things. So over on the left-hand side, we have metals and non-metals. We categorize these things based on whether they are metals. In the case of copper, right here, I'll talk about copper in a little bit, and non-metals. So for the case of this, asphalt, concrete, cement. Also, we'll look at that when we talk about architecture and building materials. Here's a non-metal, salt. And so we group them in terms of metals and non-metals. We also group them in terms of whether they're geochemically scarce. There's nothing really magical about this distinction. Geochemically scarce is less than 1/100th of 1% of Earth's crust. So platinum, for example. And then geochemically abundant. So for example, sand that we use in building materials and other things. What do we use them for? I'm not going to read this all. We use them for everything. Your, as we will see, entire home comes from a mine. If you're an artist, your art studio comes from a mine. If you're a chemist, your lab comes from a mine. Your surroundings come from a mine. And the thing with, move myself down, where can I move? I'll sit on this couch. How's that? Maybe behind the couch. No, right here, okay. The thing about mineral resources and talking about them and teaching about them is I find them fascinating. I hope you'll find them fascinating, but it is tough because it ends up being lists and lists of lists and lists of lists of lists, as you'll see. So what are the mineral resources? You can look at the periodic table of the elements that's interactive that I put on our learning management system. So for that, for example, again, we'll talk about copper. So we have a list of these different minerals. And then of that, we have a list of properties that they possess. And from that, we have a list of places we can find them. And we have a list of things that we use them for. So it can get overwhelming. But the point to this is that, as you can see at the bottom, this is the subject of this class. Everything comes from a mine. When I teach a related course called environmental geology, I go in the first day of classes and I say to the students, first thing, I'll give you an automatic A in this whole course, not just a quiz, not a homework assignment, in this whole course, if you can find an object in this room that didn't either come directly from a mine or was processed using something from a mine. And if we were in class together, I would be asking you these questions. Name something. Gypsum, wallboard. That is calcium sulfate. That's the evaporitic chemical sedimentary rock that comes out of seawater. You could just go on all day about all of this. But the bottom line is no one has ever stumped me on this. No one has ever said something in the room that didn't come from a mine. I can think of one thing, which is the topic of natural disasters, but we're not in that class. So the point here is that everything around you is geology. It all comes from a mine. So your stuff is nothing more than minerals and rocks that are created by the processes we talked about when we talked about rocks and minerals. And we put them together with energy that also is something that comes from a mine, whether it's mining for crude oil through solution mining or open pit or subsurface mining for coal. And so here we have everything coming from a mine. Move myself down here. So this is an overwhelming picture a little bit, but it is excellent, I think, because it shows that, a lot of the things that we have around us that we use for economic goods and the environment in which they are formed. So mid-ocean ridge is an igneous process, crescenary wedge, a tectonic process. So I guess you could call that sedimentary at the top up here, because as this ocean crust subducts or dives down, the sediment is being scraped off of the seafloor. So they're sedimentary. This is igneous. And as we get down into the bottom part here, you end up with metamorphic rocks because the pressure is so high, as you remember from metamorphic rocks. Magmatic arcs, so magma coming up, you have a basin, all this is being eroded and sediment is being deposited. Maybe you have a river here, a stream here, a waterfall here. And then you have a hot spot, again, some more volcanic material coming up through the lithosphere. Continental basin, you have sediments that are being sloughed off of the high points, depositing like a sedimentary rock would in the low points. And as it gets progressively buried, you can get into to metamorphic processes. And as there are fractures and cracks, hot water comes from beneath and will deposit out as the water cools. The warmer water is, the more materials and more metals can be dissolved in the water. So as the water cools, these things come out of solution. And shield, so that's a stable inner part of a continent where nothing is happening at the surface, but you can have metamorphosis going on at the bottom because it's just a thick, stable situation. Continental margin, so rift just means an earthquake essentially. So as those blocks drop down, sediment fills in. So here you have, again, a combination along this top here of igneous, sedimentary, and metamorphic processes. Here's the visual depiction of what is going on in Earth, on Earth. Here's the seafloor here too. There's some things that are very important on the seafloor here. And then the processes here that are endemic to each of these environments, magmatic segregation. So minerals cool at different temperatures. You have high temperature minerals, low temperature minerals, and that can lead to the list of metals that can be found with regards to magmatic segregation, hydrothermal sulfide. So as the water comes up, it cools. As the water cools, these things precipitate out and form deposits. So I won't read over all this. This is a good picture to see, and you have access to the PowerPoint slides on our learning management platform. But you can see that at these different locations geologically, you end up with huge lists. And you can see that the lion's share of things come from metamorphism. There's a lot of stuff that is metamorphic, and I include contact metamorphism, regional metamorphism, and also hydrothermal deposits they come from igneous processes and go into metamorphic deposits. So this is a beginning in the embodiment of mineral resources. Some of we geologists, not me, but others, geologists, their job is to know this, to know where you go, in which environment you travel, to look for these materials. And so you're looking at here is how geologists, for example, in this picture, you're in a coastal environment, you see sand swirling around here. A good economic geologist would know what you can find here. What can we go and take to use for our economic benefit? We use all sorts of things. We use seismographs, we use radar, we use sonar, we look at variations in Earth's magnetic field. You would imagine that there would be changes when there's a lot of metals, aerial photos, satellite images. Now you can just sit at your desktop and go on Google Earth. It used to be that we had to be a lot more bit of detectives to figure these things out. But we geologists spend a lot of time discovering what is where, and then thinking about how much of it is there, is it worth going to get it. This is the topic of a lab, Dig Into Mining, where we'll look at copper. So we discover these. So I'm going to talk kind of about the process of getting there. First, we know what we're looking for with regards to the previous slide. Then we go and find it. Once we discover it, we have to go get it, mining. So getting metals, getting energy, getting non-metallics from Earth's crust is the next thing we do. We do this really in three ways. First of all, through large surface excavations. Here you have a picture of the Bingham Copper Canyon mine. It's the largest mine in the world. Therefore, it's also the largest mine in the United States. It is about 1.2 kilometers deep. So it's an enormously, enormously deep mine. Again, this is something that you will look at when you look at the Dig Into Mining lab exercise. Copper, there are a lot of copper mines. The largest underground mine is also a copper mine. I'll show you a picture of that next. We use copper a lot. Copper is an amazing, amazing material. We use copper in things like wiring, in motors, in roofing, in gutters, in rain spouts, in plumbing, in cookware, in cooking utensils, in industrial machinery, so things like heat exchangers, transformers, dynamos, which are machines that essentially convert mechanical energy into electrical energy. So anything from a generator to about bicycles, a low-tech dynamo. Why do we use copper for this? Well, because it has the material properties from going down to the atomic level, which again is why we look at atomic level, that make it desirable. So essentially what it is a situation where each copper atom has lost an electron as it combines with other ones and becomes a positive ion. So copper is essentially a lattice of positive ions with negative ions moving around. And it would be similar to a gas moving around in a room, and the gas can carry things with it, or it just moves everywhere. So for that reason, some of the properties, again, with all of these lists, are that copper has excellent, excellent electrical conductivity, excellent heat conduction. It's hygienic, so it's you can use it for medical processes. It is in culinary processes. It's easily joined. You can solder it, easily joined. It's ductile, so it's able to be shaped and bent, but it's also tough. It is non-magnetic, so we don't have to worry about the magnetic aspect of it. And it's also, from an aesthetic point of view, if you're talking about jewelry, things like that, it is beautiful. It's a beautiful color. And it's also really easy to recycle it. So you can melt it down and reuse it pretty easily. So that's at the surface. Underground, you have underground mines, and we'll talk more about mining when we talk about waste. And when else we talk about this? Yeah, air pollution and solid waste. Underground mines have different problems. If you're a mine worker, you would prefer to be in an above ground mine because you're at the surface. You don't have to worry about these tunnels collapsing, filling in with water, caving in, being blocked off. So this is a picture of the largest underground mine. It's called El Teniente. It's in Chile, and they also mine copper here. And about 11% of the global supply of copper comes from this particular mine. It has enough copper in it to provide a reserve. We'll talk about reserves in a minute, for 70 years globally. So it's a huge, huge mine. In terms of underground mines, these are better from an environmental point of view because you're not destroying and taking off the whole surface of Earth and taking away all the animals and plants in the soil. But they're worse from a human health point of view. Again, you can have these gases that can accumulate. They can be poisonous in and of themselves. They can explode. They can collapse. May 2014, there was a big collapse, the Sonoma mine disaster. in Turkey. It was the worst mine disaster of the 21st century so far. About 301 people died. And so far this century alone, so far, there have been almost 9,000 people who have died in underground mines. So it's quite dangerous for humans, even though it is, sort of beneficial in terms of an environmental point of view. We also have, this is the most recent form of mining. This is mountaintop removal, pretty self-explanatory. You can see the picture right here of the tops of the mountains lopped off. Mountains are very fragile ecosystems. Going up a mountain is a proxy for going up in latitude. So it's like going from the tropical rainforest all the way up to the tundra and the Arctic zone. So you have very, very different ecosystems as you go up the mountain. Really important to preserve them. Mountains are also the headwaters for streams that serve as valuable water resources that are groundwater, surface water resources. And so this is bad. We remove it. It's referred to as strip mining, surface mining on steroids. We remove up to 800 feet of the top of the mountains to reach coal, especially. This is mostly coal that's not accessible by other methods. And it ruins the mountains, ruins the fragile ecosystem at the top. And what we do is take that stuff and we dump it down into the lower lying areas, which is where the water is, where the rivers, lakes, and streams go down through gravity. So mountaintop removal is really bad. But this is how we get things. Once we find the reserve, we drill holes into the subsurface. This gives me angst. I was once trapped, another story for another time, in a mine underground outside of about an hour and a half outside of Pittsburgh, Pennsylvania. Oh my God, it was so scary. Yeah. There was, you think of mines as they're, go into an elevator and you go down and there you are and you do your thing and you go back up. This one was a type of mine that was sort of shallow. So we got into these things that looked like roller coaster things, but they were trains and they were so small that you had to crouch down. The bigger the opening, the more expensive it is. So we went on this thing that was like a roller coaster, but it just went down, just went straight down, 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 and we were going forever. And I'm a little claustrophobic too, but I'm a geologist, and so I'm going to do that. So we get to the bottom, and we had been briefed on what do you do if there's any problems. And the guy was pretty cavalier who was bringing us. He said, I've been working down in a coal mine for 45 years. Nothing's ever happened. Okay, false sense of security. We get to the bottom, you hear this explosion. And look back, and there is fire coming from the back of the train. And the guy, you could tell, was trying to keep calm, but he was freaked out. And he said, okay, so we're going to put our training to use. So everybody walk down the shaft. And when you get to the first tunnel to the left, please walk down there. That's where there was this, it's like a big shower kind of thing where there's oxygen in it, because the problem is when fire happened, it takes the oxygen out of the atmosphere, so you suffocate. So we're going down there. Oh God, oh God. Some people don't even like to hear this story. So we went there and I used my yoga, my meditation training, and I just looked down at the floor, breathed in and out, in and out. So the guy called to the surface, but it was the last group of the day, and the person at the top left, and there's no cell phone service. So none of our cell phones worked. Finally, after a while, he got to someone, I don't even know how he did. They had to bring a special tow truck, a long time, bring it down to where we were, pull out the on fire thing. He put the fire out, but there was smoke there. Pull out the old train, bring down a new train, put us in, bring us to the surface. And I am never even going into a basement again, never mind a mine. Anyway, yeah, sorry, I saw this picture and started breaking out. So you drill in these holes and you explode the walls of the rock. There's the picture. Explosion, whether it's underground, obviously wouldn't be too close to this either way, or mountaintop removal, creates these fragments. So you're creating crushed rock, you're creating rubble, if you will. Once you take that rubble, you have big, huge machines, the largest vehicles on Earth. I know this from my 8-year-old son, are mine vehicles. So you take all this crushed rock and you put it into these explosive fragments, bring it to a crusher. and then you process it. So you're mixing it with water and you're bringing it on this conveyor belt to process it. And what you want to do is separate out the unuseful rock from the metals that are in there. And the way you do that is you have these big mills, ball mills is what this is a picture of. So there are huge rotating drums, and there are these balls in it, and there's lifting plates that lift up the material and tumble it and tumble it. And so what you're doing here is to take the larger particles and turning them into smaller and smaller particles with the intent of getting the minerals, whatever metal it is. You separate those out by various methods. You can use acid, but in this case, using soapy bubbles. You float the stuff that you're looking for to the top in these vats that look like hot tubs, if you will. This is tough when you're talking about minerals that are geochemically scarce. You have huge, as we'll see, amounts of rock that are being crushed and processed for very, very small amounts of the material that you're looking for. So we also have in situ mining, or mining without removing all the rock. So you have percolating solutions, essentially acid. So you would fix this pile of material, you put a geotextile underneath, and you have acid on it, so that percolates down the acid, it makes it mobile, brings them to the bottom, and you can get them out by drains. Regardless of what type of material you're using and you're getting, again, you're trying to take the useful and separate it from the unuseful. And so you create lots of mine tailings. Mine tailings are awful. They're environmental disasters. They can also be natural disasters. If you think about the Aberfan whales, mine tailing collapse, and other things. So this is the spent rock. You just have to get rid of the spent rock. People pile it up on the landscape, and you have these huge piles. Let's look, for example, at the picture. So first, look at the bottom left here. This is a picture. You might look at this and say, wow, it's beautiful. Let's go for a hike on that little mountain in the background and swim in this pretty bluish lake. It looks beautiful, right? This is Lake Karachay, which is in central Russia. And it is actually, those are the mine tailings of nuclear mining. So they're looking for uranium. And so separating out the uranium from the mine tailings, pile them up there next to the lake. This is the most polluted place on Earth, depending on what your metric is. If you were to stand next to this lake, the lethal dose is 30 minutes. So if you stand next to this lake for 30 minutes, you'll die. So this is a problem, obviously. And mountaintop removal, and you can see that scars on the landscape. Every step along the way, you have a scar from mountaintop removal and then processing the tailings that you put down. And in this top graph here, table here, you don't have to remember things about it, but essentially what you're looking at is by mineral, the amount of mined ore that we have taken out this is a little dated, so this is around 2000 or something. This is millions of tons. And this is the percent of ore that actually becomes waste once you go through the processes that we started to talk about and that we'll continue to. So you see in the case of gold, look at this, 99.99% of the rock that you've mined is now piled up on the landscape in some way. And these numbers don't drop off detectably in the other types of materials. So lots and lots of pilings. What do we do to keep us safe? There is the Surface Mining Control and Reclamation Act. This was of 1977. And it grew out of a concern for the environmental impacts of strip mining of coal, actually, especially coal mining, but it grayed into other types of mining. There are two programs. One regulates active coal mines and the other regulated reclaimed abandoned mine land. So what do we have to do about these mine areas to keep the public safe? So move that out of the way. So that's what keeps us safe. I teach a class called Wetlands Science and Policy here, and we talk a lot about cleaning up waste using constructed wetlands. So it's not a good idea, and it's actually highly illegal to put pollution into wetlands that are existing, but you can create wetlands. And when you convert places to wetlands, you can phytoremediate, which means to use plants. So phyto is the Greek word, which means plant, and remediate is the Latin word. I don't know why they grouped the Greek and the Latin word together, which is remedium, restoring balance. So you can use plants. Plants will, and again, this is the topic of another class. I always have to rein myself in here because I'll spend 8 hours talking about phytoremediation. But essentially, you use plants and algae to remove things like fossil fuels, so to remove crude oil, to balance pH, to remove metals, to remove solvents, to remove explosives. Here we are, lists again. You can also use them in the agricultural industry to remove pesticides, herbicides, rodenticide, fungicides, fertilizer, that sort of thing. And what you do is to construct wetlands. So here's some pictures of constructed wetlands that are being used. There's a mining operation in the background here to remove metals and acid and other things, sediment from the plant. Once you have, especially with coal, but metals mining too has a lot of acid associated with it. So once you have done what you've done up to now, you can add lime. Use treatment plants for water and for the land surface to add lime. So usually things like calcium hydroxide, lime it's like chalk or limestone. It's calcium, and then it's some inorganic material, and there's oxide or hydroxide. And essentially the chemistry, I keep saying essentially, sorry. The chemistry is such that you take the calcium hydroxide, you put in water with it, and when you add acid, so hydrochloric acid, for example, you break the HCl, hydrochloric acid, using the water, and the Cl will complex. So it's recombining with the calcium from the lime, and the H will complex with the OH, hydroxide, and turn into water. So you will be able to take the acid out of the waste, water, rock, etc. So acid is, it's really harmful, but it's pretty easily treatable. What else can you do? Once you're done with the mining, here's a mining reclamation situation. You cover it over because you don't want to leave it open to the land surface, because water can come in, precipitate out anything that's left, and cause groundwater, surface water problems, as we'll see. And then you revegetate it. You put a cap on it, you put plants on it, and you're good. In terms of mining, it's important to have a social justice and a sort of fairness component to the science of this. And the international perspective in general, especially in the developing nations, industrializing nations, is that the now highly industrialized countries, highly developed countries, have done a lot of environmental damage as a result of their mining. They're also doing currently a lot of damage in other countries when they export raw material, export from the other countries raw materials, import them into the United States, for example, and they have mining interests in other countries. No country is self-sufficient, so we all countries, need to get minerals and energy from elsewhere. So it's important to think about this, and it's also important, I think, to think about the relative amount of materials that countries use. I'll always say that the United States is 4.6% of the population and shrinking, because other countries are growing more rapidly, and we use an inordinate amount of materials. We also generate an inordinate amount of waste. So this is US Canadian consumption as a percent of world total consumption. So this is North America, essentially. And you see, minus Mexico, you see lead, 30%. We're less than 5% of the population, and we use, a quarter or more of these three, and then lesser amounts of zinc and gold, but enormous amounts. So this is, many people would say, not a fair situation. So distribution versus consumption. We need all of these things. We need them for lots and lots of things. The United States keeps something called the Strategic Minerals List. It's a list of materials, metals, of mineral resources And if we didn't have a steady supply of them, our economic infrastructure would be severely impaired. So we need a constant, steady supply of these. We need them for industrial, for commercial, for economic, for household, for everything. And they're only found in abundance in different places. Antarctica, for example, South Africa, South America, so Democratic Republic of Congo. So they're only found in a couple of places. They're not universally and uniformly scattered throughout Earth. So this requires that we are dependent on other countries. It requires political relations that are positive or warring, if you will, and robbing people of their resources. And it also leads to stockpiling for the future, because there are different reserves, and these reserves are always being refined. So it's tough, because they ask geologists, how much of this is left? Well, we don't know. We've identified some resources. Surely there are more out there. So this is a guess. They're always getting refined. But in terms of the life expectancies in these minerals, this is based on a 2% growth rate. So in the production of this, you see that these numbers may or may not mean anything to you, but over here, the life expectancy, lead, we have 17 years left. Zinc, we have 20 years left. Copper, 22 years left. This is tough. This is very tough in terms of, the things that we need to have our society run. Which should lead to the question, how can we increase the supply? Well, we can locate new deposits, because again, the reserves are our best guess, but we know there's more out there that we haven't identified yet. So let's identify new materials. Antarctica is considered a place of vast mineral resource wealth. We had a treaty put in place that's being hotly debated and trying to be repealed in the early 60s. Much of what we know about the natural resources in Antarctica, and geology of Antarctica, comes from what we know about South Africa, South America, Australia. When Gondwana, so all the continents were together, the same processes were acting on these continents. And then as they moved apart, they're now in different geographic regions, but their geologic underpinnings are the same, which means that Antarctica, even though we don't know the absolute reserves, we know that there's likely vast reserves of coal, petroleum, minerals, and all sorts of minerals, things like chromium, nickel, vanadium, copper, iron, platinum, they're all down there. So many scientists really think that Antarctica is a place of unlimited natural resource wealth. But the problem is there's this harsh climate, there's a short working season, there's thick ice. Sadly, climate change is making the ice thinner, making it easier to get down there. Means that it's difficult to get the minerals. And there's a huge cost associated with getting there, setting up mining operations, removing, transporting, and shipping things back to where we use them. So because of that, there's two schools of thought here. One, by the time it's feasible to get down there and get all of this, there will be alternatives that exist. The other is that economic pressure will force mineral and energy exploration into more and more remote regions. So we'll see what goes on with regard to Antarctica. There's also a wealth of minerals on the seafloor. So these are called manganese nodules or polymetallic nodules. They are iron and manganese, and they're rock concretion. So what that means is that there's something at the center, and they look like onions, layers form slowly over. They cover 70% of the seafloor. So this is a vast, vast repository, over 500 billion tons of these that are just pretty much pure iron and pure manganese. And again, this is just an example of places where we can go. This is a map of manganese nodules from way back in 2006. Here you are. And they occur at depth. These brown areas are where manganese nodules. It's a dated slide, but the places haven't changed and they haven't grown. So most of the stuff that we're looking at over here, this is the most promising area. It's called the Clipperton Fracture Zone. And so we could get minerals, some minerals from the ocean. We can also substitute things. We can substitute the scarce things, platinum, reasons that we'll discuss later, for other things. Change the way that we engineer things, that we create things. Glass, plastic, aluminum have all substituted, for example, for tin. So we can substitute things. We can also conserve them. Reuse. We'll talk about reuse. Really all of this. I'll just say it in passing. So we'll talk about reuse when we talk about hazardous waste and solid waste. Reusing things to the extent we're able is great. Recycling, we've been taught about recycling since we were in pre-K, correct? And we'll see, and if you haven't watched, we'll see when we talk about waste and recycling later that anywhere between 90 and 90% reduction can be reached by using recycled aluminum versus virgin aluminum in water pollution, water resources, soil erosion, energy use, so solid waste creation, mine tailings. Remember mine tailings when we talk about solid waste. It's the back end of what we're talking about now. So recycling is good. Changing our mineral requirements. So what do we need? What can we do differently? What else? This is also something I don't want to say anything about, mostly because it's very upsetting and I don't like to focus on it. It's why I have an iPhone 4. But the countries that have a lot of minerals are in bad shape with regard to social justice, with regard to the way that humans are treated. So this is a picture of some pictures of the Democratic Republic of Congo, and there are these vast reserves of wealth in this country, the Democratic Republic of Congo. We need for our iPhones, iPads, iPods, everything. We need huge amounts of cobalt, of copper, of tantalum, of tin, of gold, and there are about $25 trillion in untapped mineral deposits in this country. You would think it would be a wealthy country. No, the mines are controlled by rebel groups. There's just massive environmental degradation. There are all sorts of illnesses. There's the systematic rape of women. There's massive family disruption. So you'll see short videos on that. This is tough. Sorry that it's tough. You wouldn't think that a science class would be this tough. But anyway, so we move on, to mineral refining. So mineral refining is when we take the minerals that we've now successfully extracted from the rocks and we melt them. We use lots of energy, lots of fossil fuel energy to, so once we're done processing, to heat them. So the impact here is more mine tailings, massive air pollution, acid rain, climate change, metals are liberated, particulates go up into the atmosphere, and it is a bad step along the way. Seeing a recurring theme here. Smelters, you melt the minerals to further remove impurities, and this is a smelting furnace, and you can see that the energy that goes into this to create this temperature is massive, and we'll see more about this later. The molten metals are then poured into molds to solidify, and associated with this processing, there's been a lot of harmful gases and particulates, so suspended particles, gone into the atmosphere. Think about the beginning of the Industrial Revolution and all that went on in Britain. These days, it's a good news story. If you're going to do this, you can see that this is permitted in 1992, a long time ago. And then this is a modernized smelter. You can see that acid mist has gone down essentially by 3 times. Particulates have been halved. Sulfur dioxide has gone down by enormous amounts. So we're getting better at using modern technology to reduce the impact on the environment. And just sort of a nod to the future when we see Story of Stuff, if you haven't seen it already, and know it's really dated, but it's so important because after all of these processes, we have the raw metals and materials to make stuff, and less than 1% of all of the stuff we make is still in our house after only 6 months. Gets thrown away in this endless quest for new and fabulous and planned obsolescence. So we use Earth as the starting point for all of this stuff that we make. And then we also use it, as we'll see, as a repository. We use Earth as a dumping ground. This waste so travels through geologic reservoirs, through our air, through our water, through our soil. Sometimes we burn this stuff, and again, you'll see or have seen this in Story of Stuff. incinerators are good in that they reduce the volume of hazardous waste by 95%, but they create dioxin. So incinerators are the number one source of dioxin, which is the most toxic substance known to humans. So, and then also we can talk about the garbage patch. I put Wally here. I hope I don't get accused. I'm not selling these videos, they're just for you, but accused of copyright infringement. This is such a great movie, and it came out so long ago, and it's so what do you call it? Prescient, that it predicted the future, premonition, whatever. It's awful. So yeah, I'll tell you one last story, and then we will part ways for now. Just this morning, a student in a class came up and said, hey, well, she didn't say it. She said, what's better for the environment, to shop on Amazon or to go to the store? And told her this long story of apples versus oranges, and what kind of car do you have, and how far is the store, and how many variables go into it. And the bottom line with regard to that question is it's apples and oranges. It's 6 of one, half dozen of another. You cannot say there's a clear winner here. Packaging, material, energy. But I'll tell you also that a friend of mine called me up a week ago, and they're having a fight at work. Whose lunch is more sustainable? I have bamboo flatware and a reusable napkin, and this person has plastic, whatever, and makes the argument for it's better to just throw this away than to use the energy to wash this stuff. Whose idea is better? For that argument, which I like settling argument, I said that's a trick question, because the person whose lunch is more sustainable is the person that doesn't have meat in it. And with regard to the Amazon versus store question, it's also a trick question. The right answer is just don't buy so much stuff. Don't buy so much stuff. Don't click on Amazon, and don't fill your shopping carts filled with stuff at Target because it's cheap, because here's where we end up with less than 1% of the materials that you've purchased being in your home after 6 months of use. So I hope that this gives you an idea of the impact that the products have on Earth as we mine for the materials. And at the heart of this discussion on mineral resources is geology. Okay, I hope that this was an insightful lecture, and I will see you again soon.